record. So as part of our continuation of this lecture on structural elucidation, we're next going to cover chapter 13, which is nuclear magnetic resonance spectroscopy. It is probably one of the most powerful and ubiquitous structural determination techniques in organic chemistry for all classes of organic compound. The only technique that I would consider more powerful than nuclear magnetic resonance spectroscopy would be crystallography, but that of course assumes you're able to crystallize your sample. Anyway, so NMR is the most widely used structural determination technique and spectroscopic technique. It provides a map of the carbon-hydrogen framework of molecules and allows you to determine the relative location of atoms within a molecule. It is extremely information rich. And to help you understand what's going on when you look at an NMR spectra, it's important for us to understand the theory. Okay, so remember how when we think about like electron diagrams, we draw these up arrows and down arrows to represent our electrons. What do these arrows represent? What are these arrows trying to convey to everyone? What are these arrows trying to convey? What property? Spin, yep. So we have up spin and down spin. So a nucleus with an odd number of protons and or an odd number of neutrons possesses nuclear spin. So H1, C13, 19 fluorine, these are all NMR active nuclei. So the word spin, where does that word spin come from? It has a very special meaning in physics and chemistry, and it's this idea that a rotating or spinning charge generates a magnetic moment. So the magnetic moment can either be oriented in one direction that we'll call upspin, or the magnetic moment can be oriented in the opposite direction, and we can call that downspin. Okay, now the nuclei isn't actually spinning, but the main thing that I want you to know is that a rotating charge generates a magnetic moment. So this arrow is representing our magnetic moment, which is the magnetic field that's produced by our nucleus, in this case, our hydrogen nucleus. So a nuclei with an odd number of protons and or an odd number of neutrons generates a magnetic field. The nucleus can be either upspin or downspin based on the orientation of the magnetic field. So we can have a hydrogen nucleus that is upspin and a hydrogen nucleus that is downspin. Different nuclei have different spin values. So up and down, one's a positive value, down's a negative value, but the magnitude can be a little bit different. And that plays into a little bit of differences in signal intensity and signal frequency that we see. Anyway, does this idea of spin make sense to everyone? So we have two possible orientation of our magnetic field, of our magnetic moments for our nuclei, upspin and downspin. Does that basic idea make sense? Now, with no external manipulation, these two spin states are identical in energy. So the upspin and downspin are identical in energy. But we can leverage an external magnetic field and do something that's really quite special. So in an external magnetic field, the nuclei spins and the internal magnetic field can align either parallel or anti-parallel. to the external magnetic field. So, depending on your nuclei's spin, it will either be aligned parallel, aligned with the external field, or aligned against the external field. Now, why is this important? Why does this matter? Well, in a magnetic field, the two spin states, up and down spin, are not equivalent in energy. Because inherently, if you're opposing the external field, that spin state will be higher in energy compared to if it was parallel to the external field. So does everyone see how the two spin states are up and down spin now have a difference in energy? Now there's a difference in energy between our two spin states. And this only works because when we apply a magnetic field based on the nuclei spin, the nuclei's magnetic moment will either be aligned or opposed to the external field. And that directly affects the energy of each spin state. So we have two spin states that now have different energy. Two states that have different energy. Does this framework look familiar to everyone? Does this idea where we have two
Wait,
different...
Professor, I have a question.
Yes? Mm-hmm.
So like earlier you mentioned that they would be identical in energy in the nucleus in the
Yes,
previous
so
page.
the spin states would be identical in energy, assuming no external manipulation. They're initially identical.
Oh, okay.
When we apply a magnetic field, depending on whether our nuclei is upspin or downspin, we will see either the system. Sorry, I'm getting a little bit of reverberation. Sorry, one moment. Would you be able to mute just while I continue this explanation just for a moment?
Okay.
So essentially, in an external magnetic field, some of our nuclei spins will be aligned with the external field and will be lower in energy, while some of our nuclei spins will be opposed to the external magnetic field and as thus will be higher in energy. Thus, in an external field, our two spin states are now different in energy. Does that make sense?
Yes, it does. Thank you.
Perfect. The A side just represents no external field. While the B side represents when we have an external magnetic field, what happens to our system. Now, when we think about this separation between our two spin states, yes, the two spin states are equal in energy in the absence of an external field. Yep. If we turn off the magnet, if we turn off the external field, the two spin states will collapse to the same energy. They'll be identical in energy. However, when we turn our magnetic field on, the two different spin states with different orientations of the nuclei's magnetic moment will have different energies. Does that make sense? Does that answer your question? Okay, now, just like in any spectroscopic technique where we're measuring the absorption of light, we see that because there's a difference in energy between our two spin states, a nucleus can be excited from the lower energy spin state to the higher energy spin state by absorbing electromagnetic radiation with the exact energy equal to the difference in spin state energy. So if we, for example, if we irradiate our sample, if we expose our sample to the exact frequency and the exact wavelength of light that matches this energy difference between our two spin states, then we will be able to excite our nuclei to the higher energy spin state. So our nuclei will absorb defined wavelengths of light based on this difference in energy between our two spin states. Does that make sense? Does that idea make sense? That's often the central refrain of spectroscopic techniques. HV, so it's based on the equation E equals HV, where V is the frequency of light. Just like what we saw in the chapter on IR. In both cases, our sample is absorbing light. And by looking at the frequency of light absorbed, we can use that information to tell us a little bit about the identity of our nuclei and the environment of our nucleus. Does that make sense? Does that answer your question? So you need a pretty strong magnetic field for you to observe sufficient separation between the spin state energies. So as you increase your external field, the difference in energy between your spin states is proportional to the external field strength. So often you need some pretty powerful magnets and some pretty powerful external fields in order to get a sufficient separation. The greater the external field, the greater the energy difference in the two spin states, and in turn, the greater frequency required for you to promote your nuclei to the higher energy spin state. Okay, so based on this difference in energy between the spin states, our sample will absorb certain frequencies of light, and we can measure the frequencies of light absorbed. So the one thing I want you to know is that it takes a very small amount of energy to excite a nucleus to the higher energy spin state. And we need a strong field in order to tune this energy difference so that it's in a reasonably observable range. Does that make sense to everyone? So it doesn't take much energy to promote a nuclei to the higher energy spin state. And we can measure the frequency of light observed and the frequency of light absorbed by our sample in order to get a sense of this difference in energy. Now, at this point, many people are probably thinking to themselves, well, aren't all protons the same? It's a hydrogen nucleus. What difference could there be? Well, this is where we bring up this idea of chemical shift. And this is probably the most important concept that you need to be familiar with to navigate NMR spectroscopy. So, in an external magnetic field, the electron density surrounding the nucleus will generate what's known as an induced field. And this induced magnetic field opposes our external magnetic field. Thus, for a given hydrogen nucleus, it is exposed to the external magnetic field and the induced magnetic field generated from the electron density surrounding that proton. So if we think about this from a net perspective, so if we look at our hydrogen nucleus, it is experiencing two magnetic fields. The first of which is the external field. So this is our external field. Counter to the external field is our induced field. And if we add up these two magnetic fields that are oriented in opposite directions, we get our net external field. Now, thinking about this net external field, we can conclude two things. First, this net external field is also proportional to the difference in energy between our two spin states. Further, we can conclude that the electron density that surrounds our proton can quote unquote shield the nucleus from the external magnetic field, and in turn, the nucleus experiences a net weaker external magnetic field. So as a result, our delta E, our difference in energy between spin states, is smaller with shielding. So when we have electron density surrounding our nucleus, that electron density generates an induced field, and that in turn leads to a smaller effective net external field and a smaller difference in energy between our two spin states. And in turn, that directly impacts the frequency of light absorbed. Now, what's really cool is that the electron density surrounding different nuclei will inherently be different, right? One moment. Let's just check. Okay, perfect. It's back. So the electron density surrounding each hydrogen nuclei will be slightly different. So in turn, shielding is directly affecting the energy difference between the spin states and the frequency required to excite the nucleus. In turn, what that means is different protons require different frequencies to excite that proton to a higher energy spin state. Different protons have different electronic environments, and as a result, they have differences in energy between the two spin states. So you can have two protons. We'll call this proton A versus proton B. And as we notice for proton B has a slightly different gap in energy between its two spin states. And as a result, proton B would absorb a different characteristic frequency. So in turn, different protons have different characteristic frequencies of light that they absorb based on their electronic environment. Does that idea make sense to everyone? Does that central idea make sense?
Professor?
Yes, please go ahead.
I was just wondering, how can it be different if the hydrogen atoms are the same atom, if that makes sense?
Yeah. So let's say, for example, we have a halogen adjacent to our proton, right? The proton that's closer to this halogen would experience a stronger inductive effect, and as a result, this proton will be relatively electron deficient. As a result, because these protons are in different electronic environments, different chemical environments, they would have different characteristic absorbances and different characteristic absorb frequencies of light. Does that make sense?
Yes,
So
thank you.
NMR can allow us to differentiate protons based on their unique chemical environment. So rather than writing it in terms of frequency, we have this catch-all term known as the chemical shift, which describes the frequency of radiation required to promote the nucleus to a higher energy spin state. And different protons have different chemical shifts based on the electron density surrounding that nucleus. Okay, so we can differentiate protons based on their electronic environment. Any questions so far on this? Okay. So what is the chemical shift referring to? So the chemical shift describes the frequency of radiation required to promote the nucleus to the higher energy spin state. It has units of part per million, and typically we calibrate to a reference at 0 part per million, tetramethylsilane, or we calibrate to solvent. So there are two main types of nuclei that we see. Nuclei that have, let me find the right color for this, that have a large amount of surrounding electron density are considered shielded. And shielded nuclei require less energy to undergo a spin flip and thus require lower frequency radiation for excitation. Shielded nuclei are found on the right side of the NMR spectra, upfield at low chemical shift values. The second type of nuclei that we see in the second major category are nuclei that are electron deficient, which are called deshielded nuclei. Deshielded nuclei require more energy to undergo a spin flip and thus require higher frequency radiation for excitation. Deshielded nuclei are found on the left side of the NMR spectra, downfield at large chemical shift values. So here's a correlation. So these protons in red would be downfield and deshielded, while the protons in green would be upfield and relatively shielded. The upfield protons are the methyl protons adjacent to our ketone, while the downfield protons are the methyl protons that are adjacent to the ester oxygen. As you notice, the reason why these protons are further downfield, they're more closely adjacent to an electron withdrawing atom, and as a result, they experience a greater inductive effect. So there are protons attached to this ester oxygen. Sorry, the protons in this methyl group attached to the ester oxygen are more electron deficient, and as a result, they appear further downfield at larger chemical shift values. Does that make sense to everyone?
Professor, what do the terms downfield and upfield mean? Oh,
Sorry.
I'm sorry, never mind. I answered my own question.
So downfield, these are protons on the left-hand side at large part per million values, while upfield protons are on the right-hand side at small part per million values. Does that make sense?
Yes, thank you.
Perfect. So you can also see this effect for carbon nuclei. So if we look at the carbon-13 nuclei, we also have downfield carbon nuclei. This is the carbon directly attached to our very electron withdrawing carbonyl functionality, and carbons that are upfield. That would be the carbon that is attached to our ester oxygen. Do the definitions of downfield and upfield make sense to everyone? And is everyone starting to relate this idea of shielding and deshielding with ideas of electron density?
So the methyl closer to the double bond oxygen is more shield. Like, is it the double bond that's making it more shielded, or is it?
Rather than thinking about something causing shielding, think about electron withdrawing groups as leading to deshielding. So when you have
Gotcha.
close to electron withdrawing groups, they're deshielded. And so by comparison, other groups appear more shielded. Does that make sense?
Yeah, so like the methyl that's de-shielded is more likely to leave. Is that what you're saying? Or
It can't be related to like capacity to leave, but you can say, for example, these hydrogens, which are on our downfield methyl group, are more electron deficient because this oxygen is a very strong inductive withdrawing group and it's very closely attached and it's very close to our methyl hydrogens. Does that make sense?
okay, so since the other methyl is connected to a carbon,
Yep.
it's okay. I
The
see.
inductive effect is weaker, and that's why we see a weaker de-shielding effect. And we'll talk
Gotcha.
about that in a moment. Does this idea make sense to everyone so far?
Professor,
Yes.
can that also be because of the oxygen, because they're the electron withdrawing group, because they're electron negative?
Yes, that's exactly right. The oxygen's electron withdrawing, it pulls the electron density away from the carbon atom, which in turn de-shields the hydrogens attached to this carbon atom, and in turn sends our proton chemical shifts further downfield. It de-shields these protons. Electron withdrawing groups de-shield protons that are connected or in close proximity in the structure. Does that make sense?
Yes.
Perfect. Any other questions on this picture? Any other question on these concepts?
Professor, is it safe to say that unshielded atoms are going to be are kind of like partial positive, so because they're
So de-shielded nuclei are generally more electron deficient.
Okay.
Yes, that is correct. So you can relate this idea of electron deficiency with downfield and de-shielding, or downfield and de-shielded nuclei. Does that make sense?
yes, thank you.
Perfect. So let's keep going. So there are a few main characteristics of NMR spectra that we're going to look at in detail. The first of which is the location and the chemical shift of each signal indicates the electronic environment and relative amount of electron density surrounding each proton. Different protons attached or adjacent to different atoms and functional groups have unique chemical shift ranges. Further, the area under each signal indicates the number of protons generating that signal at that chemical shift. Finally, the shape and splitting of each signal indicates the number and grouping of adjacent protons. So NMR is very electron rich. Very information rich. Sorry about that. And as a result, by paying close attention to different features of the NMR spectra, we can derive a lot of information about our structure. Okay, so the first idea that we need to bring up is this idea of chemical equivalence and unique signals. So two hydrogens that are in identical environments will have the same NMR signal. We call them homotopic protons. The best test that you can do for this is to replace each proton with a group X. If they give identical molecules, then they are equivalent. So for example, if we compare these two prospective protons, A and B, if we want to figure out whether or not they're chemically equivalent, we replace them with a group D. As we notice, if we compare these two structures are identical. And as a result, our two protons are homotopic. They're chemically equivalent and they would be part of the same signal. Does that make sense?
Can you explain like the homotopic hydrogen again?
The homotopic hydrogens have the identical chemical environment and will be part of the same NMR signal. So for example, these two hydrogens, because they're homotopic, will be part of one signal that contains two hydrogens in that signal.
Oh, so like the homotopic hydrogens will be in the same peak?
Yes, exactly. They're perfectly indistinguishable. Does that make sense?
How are these two like molecules identical? Because I don't really see it.
So it's identical via rotation. So you can try making a model of this structure. We can also look at it from the perspective of like a 3D perspective for this molecule. Okay, so if we take this structure and we rotate our carbon-carbon bond, we can generate so if we rotate this carbon-carbon bond, we can generate a structure which has our group D in the back, the hydrogen in the front, and the other hydrogen up top. So as we can see, these two structures are equivalent via rotation of our carbon-carbon bond.
Oh, okay, I see it.
Does that make sense?
Yes, thank you.
Generally, if you have two identical substituents on a center, then that center, it likely has a axis of symmetry of some sort. So another criteria for chemical equivalence that you can use is that two protons are chemically equivalent if they can be interchanged via a symmetry operation, such as rotation or reflection. So for example, if we look at a propyl group, N-propane, for example, and we're comparing these two protons, A and B. If I rotated this structure 180 degrees, lo and behold, you would end up with a structure that looks something like this. Now, without me putting the labels on, is there any difference between this structure before and after rotation? Are these two protons distinguishable, or are they identical?
Identical?
They're identical, exactly right. And we can extend this to this idea that this group of protons and this group of protons are all identical. They are chemically equivalent. Does that idea make sense?
So in the previous thing that we were talking about, would our peak be represented by 3 hydrogens or just 2? Because, or
For which one?
for the, if you scroll up, like what we were talking about before.
Yep. Yep.
So there's 3 hydrogens on that carbon, but we're only talking about 2 of them.
Yes. So if you were looking at the spectra for this, so to break it down, all of these 3 hydrogens are identical.
Okay.
They're chemically equivalent. And we can take this one step further in that all 6 of these hydrogens are identical via symmetry, right?
Yes.
Structure has an axis of symmetry. It's interchangeable via rotation. So you'd see one giant signal that integrates for 6 hydrogens.
Okay.
One signal that has all 6 of our hydrogens.
And is it important, or are we going to go more into depth of the deuterium thing or no?
So the D is just an arbitrary group. It's not deuterium. It's just an arbitrary group that we use to look and see whether these two structures are identical. So D is like a test group.
Okay.
Does that make sense?
Yes. Yes. Thank you.
Perfect. So building off this idea, so these two sets of protons are identical. So we'd see one signal that integrates for how many protons? How many protons would be in this signal for these two methyl groups? How many protons would be in this signal?
2.
6.
We have two groups of 3, so 2 times 3 gives us 6. Does everyone see the 6 protons? We have someone mentioning 2. Are you talking about these two here?
Yes.
Yes. Okay, so that's our other set where we have 2 hydrogens that are chemically equivalent, which are these 2 hydrogens right here. They're chemically equivalent because they're interchangeable via rotation. So it's really important to identify symmetry and to identify chemically equivalent protons. Does that idea make sense to everyone?
Yes.
Perfect. So continuing on with this, enantiotopic protons, these are very special, are protons that have an identical chemical environment, but when replaced, give a series of enantiomeric compounds. So for example, looking at the following compound, we have 2 protons, A and B. If we replace these 2 protons, we notice that the configuration at our stereocenter are exact opposites. These 2 structures are non-superimposable mirror images. These are non-superimposable mirror images, and we call these 2 structures enantiomers. Does everyone see how these 2 structures are enantiomeric? They have a single stereocenter, a single center with 4 unique substituents, and they have the exact opposite configuration at every single stereocenter. Does that make sense? Perfect. Now, enantiotopic protons can also be thought of as protons that are interchangeable via reflectional symmetry. So do you notice how we've taken this molecule and we have reflected it across a mirror plane? It's as if it's as if like, just like you put your hand up to a mirror and the mirror image is directly projected onto the mirror. It's the same idea. The D group can be assigned with any arbitrary priority that you want. It would lead to the same conclusion. I generally like to call it either the highest or very lowest priority, just for consistency.
Are these protons still considered homotopic?
So they have the same chemical environment in most solvents. So they're like homotopic protons, but this subtle distinction is important because there are ways to distinguish enantiotopic hydrogens under very special conditions. Think of it sort of like, think of enantiotopic hydrogens sort of like prochiral hydrogens in a way. Like from 112, remember how you talked about prochiral hydrogens that when replaced would give a chiral center? It's the same exact idea, except enantiotopic hydrogens are 2 hydrogens that when replaced would yield enantiomers. Does that make sense?
Sort of, thank you.
So this may seem like a subtle distinction. In most cases, they're functionally equivalent to homotopic protons for most practical NMR spectra, but it's important to bring up these enantiotopic protons because there are ways to tell enantiotopic protons apart.
Professor,
Yes.
for that compound right there on the very last one at the end of that page, will we see 3 peaks then?
Yes. So these 3 hydrogens are equivalent. These two hydrogens are enantiotopic, but will be part of the same signal. They have the same chemical shift and same chemical environment. And we have one proton from the alcohol. So we'd see three signals. We'd see our alcohol, we'd see our methylene group, and then we'd see our methyl group.
So in the spectra, oh, go ahead, Maureen.
And the H that is connected to oxygen will be the one that is the most shielded out of all these hydrogen because it's connected to an oxygen, correct?
Yes, yes. Though it gets a little more nuanced than just electronegativity when we think about chemical shift, that is a perfectly reasonable line of logic. That's perfectly reasonable as a first pass. There are two other effects that we'll talk about that impact chemical shift that we'll cover as we look at the chemical shift table. And it partially is to explain why aromatic rings and alkenes and alkynes have very abnormally downfield protons compared to what you would expect. But yes, the logic talking about electron withdrawing capacity and the fact that oxygen is a very electron withdrawing group, so the proton attached to oxygen should be downfield, that logic is perfectly reasonable. Does that make sense?
Yes, thank you so much.
Perfect.
So in the spectra, there wouldn't really be a distinction between enantiotopic versus homotopic?
Yes, so you can't tell them apart in achiral solvents. But if you have a chiral solvent, then they would separate. Then they would have slightly different chemical shifts in a chiral solvent. That's a relatively esoteric technique. The reason why we talk about enantiotopic protons is it brings up this next follow-up idea, and this type of proton you do need to be very familiar with, and it's this idea of diastereotopic protons. These are not chemically equivalent, and as their name stem would suggest, diastereotopic protons are two protons that when replaced would generate a set of diastereomers. So when we have a stereocenter adjacent to two protons, A and B, you notice that when we replace A and B, replace our protons with our test group, rather than generating a series of enantiomers, we are generating a series of diastereomers. Does everyone see how these two test compounds are diastereomeric? They're different at one or more, but not all of our stereocenters. So remember, diastereomers have a different configuration at one or more, but not all. Does this seem familiar from 112? Does this definition of diastereomers look familiar? So diastereotopic hydrogens, when replaced, would yield a set of diastereoisomers. Diastereotopic hydrogens are chemically unique. They have different chemical shifts and they have different splitting patterns. Does that make sense?
Professor, can you please clarify again on what you wrote, like different configuration at what?
At one or more, but not all.
Thank you so much.
Yes. So essentially, if one or more of the stereocenters are different, but not all of them, then you have diastereomeric compounds. Does that make sense?
Yes, thank you.
Perfect. So why is this important? Well, each chemically unique proton generates a unique signal. And as a result, chemically equivalent protons generate a single signal with integration equal to the number of chemically equivalent protons. Any questions on this idea of homotopic enantiotopic, and diastereotopic protons.
So it would be necessary for there to be at least 2 stereocenters for this case.
For diastereotopic, at least one and one prochiral center, right? The center
Oh,
with the hydrogens is prochiral. It's not a stereocenter yet, but it can be upon replacement.
okay.
Yeah, so this generally diastereotopic hydrogens appear at prochiral centers. Does that term seem familiar to everyone? Prochiral center, a center that when you replace a proton with another group, it becomes a chiral center. Does that sound familiar to everyone? Perfect, perfect. Any other questions on this example and this idea? Okay, so let's try to apply what we've learned to this example and ask how many unique proton NMR signals would you see for the following compound? Well, this compound is symmetrical via rotation. I have a set of 2 hydrogens that are in the same chemical environment, 3 hydrogens that are in the same chemical environment, and I notice that by rotation, this pair of 2 hydrogens is identical to the pair of 2 hydrogens on the right-hand side of my molecule. Does everyone see that? That these 2 hydrogen sets are equivalent? How they're indistinguishable via rotation?
Yes.
By the same token, these 3 hydrogen groups on each side are also identical. And as a result, we would conclude that we would see 2 signals. We'd see one signal that integrates for 4 hydrogens, because we have 4 equivalent hydrogens, and then another signal that integrates for 6 hydrogens from these 2 methyl groups being chemically equivalent. Does that make sense? Yes, did someone have a question?
So are we just considering the hydrogens when we're drawing these peaks?
Yes, so
Okay.
we're looking at proton NMR signals. So unique signals come from chemically unique protons or protons in a unique chemical environment. Does that
Okay,
make
thank you. Yeah.
perfect? So let's try to apply what we've learned to the following 2 examples. So for A and B, I'd like you to tell me in these 2 examples, how many unique signals would we see? And if you could label those unique signals using the annotate tool. So label what protons are responsible for each signal. To answer the question in the chat, integrations are a little more complicated. You can't just cut triangles in this case due to the way that each signal is split. So it's typically done by a computer program where they integrate each signal and then try to find the smallest ratio. Okay, so let's try to work on these examples over the next 3 to 4 minutes. And let's try to determine how many chemically unique signals would we see for A and B. And if you could try to label the chemically unique protons and sort of number the chemically unique protons in each of these structures using the annotate tool, that would be very helpful to advance our discussion. So if we think about these aromatic protons, and if we think about symmetry, you're correct in, wait. So looking at this carbon here, is there a proton attached to that carbon if we're following the octet rule?
Oh no.
So erasing that and looking at the remaining 5 protons we have, are any of those protons equivalent? Are any of those protons chemically equivalent? Any of those protons identical via symmetry? Can we draw a plane of symmetry? I have some students typing yes, yes, that is correct. So let's try to draw the plane of symmetry. So one student mentioned if we bisect this molecule down bromine, we in turn end up with pairs of identical protons. So for these 2 protons are chemically equivalent via symmetry. Likewise, these 2 protons are chemically equivalent via symmetry, and this proton is also chemically unique. So how many unique signals would we see? How many unique signals would we see? 3, exactly. 1, 2, 3. Does example A make sense to everyone? So to conclude, we see 3 signals. A signal for 2 hydrogens, a signal for 2 hydrogens, and a signal for 1 hydrogen. What about B? How many unique signals would we see for B? So we have some students mentioning 3, some students mentioning 4. And when we try to draw it out, for those who say 3 and 4, could you offer an explanation? Could you label some protons to help me get a sense of what you're thinking as you work through this problem? You can also talk it through as well or type it in the chat, and I'd be happy to convey your response and logic using the class whiteboard. So one trick that we often use is, right, we can think of like a methyl group. Like we always tacitly assume these methyl hydrogens are equivalent, correctly so, because they're identical via rotation, right? So if you have something with 3 of an identical group R, all of those R groups will, if they're the same, will be chemically equivalent, right? So by the same token, if we look at each of these methyl groups, are these methyl groups chemically equivalent? Are these methyl groups chemically equivalent? What do we think?
Yes.
Yes, exactly. So we have one signal that contains 9 protons. We have a 9 hydrogen signal, and then we have a 3 hydrogen signal. Does everyone see how we would only have 2 unique signals for this structure for the proton NMR?
So where is the line of symmetry where you have like 2 equal sides? Is there one?
So yes, there is. So in this case, rather than just like a simple plane of symmetry, we have rotational symmetry, right? So we have our 3 alkyl groups, and no matter how we rotate it, so let's look at these methyl groups, right? So I'm going to rotate these methyl groups. trust me, I rotated the methyl groups. Can we tell the difference after rotation?
No.
We
No.
can't. Yeah. So then these methyl group protons are all chemically equivalent. And they're all part of the same signal that shows up at around 9 hydrogens. Does that make sense?
Yes, it does. Thank you.
Perfect. Any other questions on this example? Any other questions on this example? Okay, so let's keep going and let's look at one more example. How many unique protons would we see for this structure? And be really careful when you think about rotational symmetry. I see some students typing 1. What does the rest of the class think? Don't be shy. I see another student typing 1. What does the rest of the class think? We have a ton of people here, so let's try to get a few more responses. So I have 3, 2, 1. We have quite a range, but they're centering around 1. Okay, let's think about it. So we have all of these methylene groups, right? Is there any difference between these methylene groups? Any difference at all that we can tell between these methylene groups? Anything that we can distinguish? If we rotate this molecule, will the methylene group that we end up with be exactly the same?
Yes.
Yes. So in general, we'd see one signal that contains 10 hydrogens because all of these methylenes are equivalent. Does that logic make sense? Perfect. So let's try to answer the following questions. Are the following protons chemically equivalent? So let's look at examples A and B, and I'd like you to tell me in each of these two cases, are the indicated protons shown chemically equivalent? Are the drawn protons chemically equivalent? Let's take about 3 to 4 minutes to work through these examples, and then don't be shy to share your responses in the chat or verbally. Does anyone have a comment for example A or B? What do we think about these protons? Are these protons chemically equivalent or not? So we see a lot of students saying A, the protons are chemically equivalent. We can bisect the molecule in half, and we note that these two protons can be split by an axis of symmetry. And they're also identical via rotational symmetry. Does everyone see how they're equivalent by rotational symmetry? How if we rotate this molecule about this axis, they're identical? Okay, so A, they are chemically equivalent. Yes, they are equivalent. For B, what does the class think? Are these two protons chemically equivalent in B? So I see a lot of people typing no, and you're perfectly right on that. If we try to draw a plane of rotational symmetry, there is no plane of rotational symmetry. These two protons are unique.
Professor, I have a question.
Yes.
So, if this problem was like on a quiz or a test, and then we would just say that there's no plane of symmetry and each one is unique, would that be an enough explanation?
Or you can show the results of the substitution test.
Oh, okay.
We can clearly tell that these two compounds, are diastereomers, right?
Yeah.
So then as a result, these two protons would be unique because these two protons are diastereotopic.
Okay.
Does that make sense?
Yes.
Any other questions on these first two examples? Now let's look at one that's a little bit interesting. For C, are these two protons chemically equivalent? And you may want to try the substitution test to verify your results. So I see a lot of students typing no, they are not the same. One student asked, could you explain the substitution test again? So if you have two protons that we'll call A and B, you replace these protons with a group X. Okay, so I'm going to replace proton A with a group X. You then try and draw a structure where you replace a group B, your proton B, with your group X. And as we can tell, are these two structures enantiomers or diastereoisomers after the substitution test? Are these two structures, and by extension, are these two protons, diastereomers, enantiomers, or what are they?
Are they enantiomers?
So enantiomers would have a different configuration at every single center. Is that true in this case?
Oh no, so they're diastereo.
Yep, these are diastereomers. And as a result, these two protons are diastereotopic. And what do we know about diastereotopic protons? Do they have the same or different chemical shifts? Are these two protons unique if they're diastereotopic protons? Yeah, they're different. These are unique protons. Does that idea make sense to everyone?
Professor, I have a question. So for example A, how come we didn't do the little wedge and the little line for that one?
Because there's no other chiral center in the molecule. And because there's no other chiral center, the molecule is perfectly symmetrical, even after substitution.
Oh, okay. But
Does
since
that-
there was in letter C, since there was that little wedge, the chiral.
Since there's another stereocenter, that means that after substitution, the proton that we choose to replace will yield two different but diastereomeric structures. Does that make sense?
Yes.
Perfect. So we're going to discuss chemical shift next class session. This is a good stopping point. I want to do a few announcements related to the lab period and point you towards a few resources, and then give some time in the lab period for students to get feedback on different parts of their pre-lab So what we're going to do is we're going to pause the recording.